Hey guys, this video is on real gases and the van der Waals equation. By real, I mean non-ideal gases, gases that do not obey the ideal gas law. So the compressibility factor, symbol Z, capital Z, it's a measure of how close a gas is to behaving like an ideal gas. Z, okay, we calculate Z for exactly 1 mole of a gas, so N is equal to 1, and so PV equals nRT, which means that for an ideal gas, PV over RT should equal 1. And so when we measure PV and T for a gas and plug it into this equation here, the farther it is away from being equal to 1, the less ideal that gas is behaving. Now the conditions under which a gas deviates from ideal behavior, and this is important to remember guys, are high pressure and low temperature. Now if we think back to the kinetic molecular theory, this makes sense. Remember the picture is that these particles are moving around really fast, random directions, straight lines until they hit something. When they bounce off, the collisions are elastic. They do not interact with each other and they take up no volume themselves. Molecules do. That's the kinetic molecular theory. Real gases, of course, do take up some volume and they do interact with each other. So at high pressure, what happens is that gas is compressed. Those molecules are forced to be closer to each other. There's less empty space, and so for one, more of the space is taken up by the actual particles, and two, because they're closer to each other for longer periods of time, they have more chances to interact. And at low temperatures, they're on average moving slower, lower average kinetic energy, which means once more they have more opportunity to interact with each other because they're in the vicinity of each other for a longer period of time. So in this graph here, you got to look at this carefully. The x-axis is the pressure in atmospheres, but I mean the first mark after 0 is 200 atmospheres, which is incredibly high. If you were to expand this and look up at normal pressures like 1, even 2 atmospheres, these lines would be straight. But at higher pressures, we see this deviation from ideality. This is Z, the compressibility factor here, and so it should equal 1 for an ideal gas. All right, so what do we do then? Well, we have an equation called the van der Waals equation. And the van der Waals equation takes into account non-ideal behavior. Now, there are many other equations, but they get more and more complicated. This actually does a pretty good job of taking non-ideal behavior into account. So if you look at the form of this equation, it should be familiar after you look at it for a while. Then the left set of brackets here, that's a pressure term. The second set is a volume term. So this looks like PV equals nRT, the ideal gas law. Only we have these corrections in here. Van der Waals did this. In the first set of brackets, this is a correction to the pressure. So first of all, the P in this equation here is the actual pressure, the pressure that's measured experimentally. And so to make this fit the ideal gas law, or to look like the ideal gas law, we're going to have to add something to it. And that we can explain in terms of the kinetic molecular theory also. Because the real pressure we expect to be lower, well, at least due to the fact that the particles actually do interact. The attractive interaction between these particles will slow them down as these guys are zooming around, moving around inside that container, and they come close to each other. In reality, they will interact, and the attractive interaction will slow down that just enough for them to start pulling each other together. And that means that now these molecules maybe slow down a little bit, or they're not hitting the wall as often, and so the pressure inside of that container we expect to be a little bit lower. That's this P right here. So to make it fit the ideal gas law, we'd have to add a correction term to it, which is this here. This A here is the van der Waals A constant, and this is, again, just like the ideal gas law, N is the moles, V is the volume, and this whole term is squared. I'll talk about the constants in a minute. Now this second term is the volume term, and notice this is a subtraction here. So this is the volume, the actual volume, and this is the volume in the brackets that we would get from the van der Waals equation. Excuse me, the ideal gas law. It's a subtraction because the real volume is going to be slightly bigger than the ideal volume, because in the real volume, those particles of gas actually take up some of that space, and so the volume we expect to be increased a little bit. And to get it back to looking like the ideal gas law, we have to subtract that away. And this B here, so N is the moles, B is the van der Waals B constant, it takes into account the actual size of the particles. So the A constant takes into account the attractive interactions between the gas particles. So the larger A is, the van der Waals constant A for a particular gas, the more strongly they actually interact. And the B constant takes into the size of the particles. The larger the B van der Waals constant is, the larger the molecules of gas. So this down here is a table of some van der Waals constants for different gases. A, for helium, A here, B here. Water, A here, B here. The units of the constants, are the van der Waals constants, are such that everything works out, basically. So because we have moles here, liters here, so we have moles squared, liters squared here, and we have atmospheres here, this whole term has to equal atmospheres because we're adding it. So van der Waals A constant is atmospheres times liters squared per mole squared. Liters squared, mole squared cancel, get atmospheres. Likewise, for the van der Waals B constant, the units are liters per mole. Because we have moles here, they'll cancel with the B constant and giving us liters, and we're subtracting this from the volume. So this is the van der Waals equation, guys, and it's pretty cool. Let's use it. So here's an example. We're going to calculate the pressure exerted by 0.2141 moles of carbon tetrachloride gas. So we're talking down here, there's the A, there's the B, at 280.5 Kelvin. That's the temperature in a 1.183 liter container. That's the volume, using both the van der Waals equation and the ideal gas law. There's going to be a difference, so explain the difference. Here's the van der Waals equation. You guys should know the ideal gas law. There's the constants. Go ahead and work this out. Get the two pressures. So first of all, the first thing you're going to have to do when you do the van der Waals equation is do a little bit of algebra and solve for the pressure. Now, real quick, the van der Waals equation ends up being cubic in volume and cubic in number of moles. N and V are cubic in this equation. Chem 101, I don't ask you to solve cubic equations. You get to Chem 102, yeah, maybe, but at this point, so you're not going to have to solve cubic equations, which means that I will not ask a van der Waals equation problem that asks you to solve for either N or V. So P or T, basically. It's usually P, pressure, which is what we're doing here. All right, so guys, go ahead and work this out. Pause the video. When you finish, when you get an answer, come on back. Welcome back. All right, so first, the ideal gas law should be pretty familiar. PV equals nRT, P equals nRT over V. Listing our constants, our variables, N, T, V, and R. So I'm using this value of R. Important to point this out. The one that has atmospheres in it, liters atmospheres per Kelvin mole, 0.08206, because if we go back and we look at the van der Waals constants, the A constant has atmospheres in there. You can calculate or look up these constants where this is in torr, but they're going to have a different value. So the ones we use have atmospheres, so we're going to use atmospheres for our pressure, which means we use this value of R. So just plugging in nRT over V, we get 4.166 atmospheres exerted by this gas according to the ideal gas law. Now let's go look at the van der Waals equation. So first thing we do is we rearrange it, solve for P. So basically divide by V minus NB and then subtract A N over V squared from both sides. Same N, T, V, and R as we had before. The A constant for carbon tetrachloride is going to be 20.4 atmospheres liters squared per mole squared, and the B constant will be 0.138 liters per mole. So we're going to plug these guys in now. So nRT over V minus NB minus A times N over V squared. Now, if we look at this equation, it gives us some good information, guys. This term right here, the first term on the right-hand side of the equal sign, this looks just like we would calculate the pressure for an ideal gas like we just did, nRT over V, except we have this minus NB in the denominator. So that means that the volume that we divide by will always be smaller than the volume we would get from the ideal gas law, meaning that the pressure from this term is going to be higher. And if we look at that, so this term here ends up giving us 4.272 atmospheres. That's a little bit larger than we got. I think we got 4.166 atmospheres. So the pressure did increase for this set of conditions for this gas by some, right? But this second term here, okay, we're going to subtract from that. So we're going to decrease the pressure by this much, and this is what comes from the attractive interactions here. And we end up getting 3.604 atmospheres. And that's significantly less than what we calculated with the ideal gas law, meaning that under these conditions, for this gas, it really is behaving fairly non-ideally. So we want to explain this, okay? So part of the problems that asked us to explain this. So ideal gas law, 4.166 atmospheres, van der Waals 3.604. So we saw in the first term on the right-hand side of that equal sign that the volume of the molecules actually did increase the pressure slightly. But the attractive interactions, the second term, the minus A n over V squared term, had a much larger effect. We subtracted 0.668 atmospheres. And that means that the pressure overall was lower than that predicted by the ideal gas law, about 13%, which is definitely significant. Well, there you go, guys. That's all there is to it.